okay.
So, infinitely many multiple Lagrangians with the first.
Hi, thank you very much for the organizing. It's a pleasure to be back here in Berkeley and be talking in this conference. So yeah, I'm going to talk about infinitely many monotone Lagrange tori in the Pezzo surface. So it's okay. First time. So, but well, just for the sake of completion, I'm going to define what does it mean to manifold to be monotone in case someone hasn't seen it. So we say that the simplex manifold is monotone if at least when restricted to pi2 of x, we have that the symplectic form is positively proportional to the first term class, and the Lagrangian is said to be monotone if now any disk with boundary on your Lagrangian has its symplectic area proportional to the Maslov index. And an important point here, I'm always going to be speaking about orientable Lagrangian. If I forget to say the word orientable, assume that, and then the Maslov index of an orientable Lagrangian is always even. So, so the examples, well, a few of examples that we have, it's in the monotone toric case. If you take the barycenter of the moment polytope, it's gonna be a monotone Lagrangian, and these here are all the examples of a Fermi manifold that's at the same time toric and monotone. Here we see that we could perform still some toric blow up on this degree 6 Pezzo surface, but if we try to force it to be monotone, which means that we will have any specific, so the exceptional curve that we're going to get there should have churn 1, and then we would have to have a specific symplectic area for that curve, and that symplectic area should have, in this case, the finance with respect to 2 here. We would not be able to keep toric while doing this blow up. And so one of the points of my talk is that, well, you cannot perform a monotone blow up and keep toric, but you can do the next best thing, which some people have commented here about almost toric fibrations. If you allow yourself to be almost toric, you can still perform monotone blow-ups and stay on this say almost toric category. So if you have seen any of my talks before or the me talks on this subject, you have seen this history, so you don't need it. But I'm going to repeat anyway. So in 94 was the first time where so we have one of main examples of a monotone torus is just the product of circles with same radius inside Cn, and was only 94 that Chekhanov created a new example of some sort of twisted torus that's not Hamiltonian isotopic to this product torus. And these tori, they have manifestations in some compactifications of Cn, like Cpn and the product of Cp1s, and these and they remain different up to Hamiltonian isotopic in these compactifications. And then in 2010, with Schlenk, they generalized their idea, but essentially, as I said, the Chekhanov torus is somehow a form of like taking a torus on a lower dimension and twist it in one dimension higher. So if you have more dimensions, you have more freedom to do different twists. So this is kind of like a bit of a generalization of their idea there. And we'll only give new examples if n is greater or equal than 3. So then in 2013, actually was my I started thinking about I don't know, perhaps in 2012 that Galkin met Denier by working on these mutations of the superpotential of the mirror that they had. They understood that how the superpotential should mutate. They predict that there should be a torus in CP2 with this enumerative geometry that bounds 41 disks if you count with multiplicity in 10 different classes. And what I did in my case was to construct such a torus and prove that you can actually get a monotone torus with this enumerative geometry. And because of the monotonicity condition, I call this a little bit already standard on the symplectic world, that if we have, you know that the minimal area of the holomorphic disks are the ones that have Maslov index 2, so they will survive. They will not have any bubbling when you deform them, because it would create some Maslov index 0 disk, but this cannot have area by the monotonicity condition. So the number of Maslov index 2 disks now becomes an invariant of the formations of monotone Lagrangian tori. So because they bound many more disks than the Clifford torus and the Chekhov torus, I can conclude that they are not Hamiltonian isotopic. And in 2014, Denis also came up with a proof that there exists infinitely many monotone Lagrangian tori in C3. And a little bit later, I finished with my. So here, the torus has this weird name. It's related with Markov triples. We have seen here already on this conference mentions to these equations. And I already predict that there should be infinitely many there, but not at the point I had a proof for that. And then I wrote a proof that they are that these tori that are constructed before, they are actually not Hamiltonian isotopic to each other. And so here we have infinitely many tori in CP2. We can think of them under the Hopf math, the lift of them to S5, and we can ask if these tori are distinct than the ones that Denis created. And by looking again at the enumerative geometry of this tori, we see that the classes that they bound disks, they definitely have different. They are definitely different. And now this year I finished writing my paper where I proved that there exists infinitely many Lagrangian tori. I could conclude it easily for this space P1 and P1 and K blowups of CP2. I could also so for K equals 1, I had to use a little bit different strategy to prove that they are different. And I mean, I constructed infinitely many Lagrangian tori for many of them, but for all of them. But my technique didn't allow me to show that they are different. But now, with the theorem of Tokanov-Paskalev, one can also conclude that they are different for K equals 2. So there are infinitely many Lagrangian tori in all the Pezzo surface. Okay. So here, as I said, this is the description of the count of Maslov index 2 disk. So at that point we had the knowledge of the wall crossing formula, but at the time that I proved for CP2, I couldn't say that the Laplace formula would actually give me the count of Maslov index to disks with boundary on this tori. So what I had to do was to instead describe this, what I call boundary Maslov to convex hull, which is essentially the convex hull of the Newton polytope of the superpotential. And what's going to happen is that for this tori here, that are indexed by the solution of these Markov triple equations, I can prove that the convex hull precisely has affine lengths A, B, and C. As also
do these numbers correspond to the Lagrangian degeneration?
Yes, the Lagrangian degeneration of two, and then we'll see that the same thing will happen for kind of all the plus surface. And for, I mean, in case of degeneration to weighted projective space, we need to have k squared before in the 5. So a lot of people already spoke here about Margaret Symington. Unfortunately, her name is not so. But Symington gave her work. She defines almost toric fibrations, and but the way I like to present it is with an example that was given by Denis when we consider this, for instance, this map in CP2, and we see that we have this S1 action such that the orbits remain on the fiber, and then in other talks we have seen this as well. We can take parallel transport around the circle in the base, and this, because the moment map is going to be invariant, these close-ups to give a torus, a Lagrangian torus in CP2. So then we see that we have different heights. So what I want now is to use this auxiliary left-sided pencil to foliate my my CP2 with Lagrangian tori. So so over the same circle lies an R family of one-dimensional family of tori that can be distinguished by looking at the moment map of this S1 action, and then we see that if you now take at the level where the moment map is 0, if we take the torus, what projects to the red curve, we see that here on the fixed point of the action, we're going to get a singular Lagrangian torus. So the almost toric fibration is like they allow the same singularities as the toric one, where we collapse the whole circle or we collapse everything to a point. But we also allow a nodal singularity. So the point is, now if we take different foliation of the base of this auxiliary fibration, and we loop by the corresponding foliation on CP2 of this Lagrangian tori, we are going to get distinct almost toric fibrations. So if you take this basic one, we can just see that here on the base we also have this S1 action, and then we will actually induce a torus action on the Lagrangians on CP2, and this is precisely the torus fibration that's given by the standard torus action on CP2, and now if we have, but now if we instead of if we take now circles that collapse to this conic here instead of we are going to get one of these singular fibers. So if we look to the base of this, if we look topologically to the base of these fibrations, what we have is that over each circle here, we're gonna have tori. Over the red circle, and at one height, we're gonna get this singular fiber. And then when we collapse here, here at infinity, each torus in each one of their heights are going to be collapsed to a circle inside the line z equals 0. And then similarly, when we degenerate the curves towards this point here, each torus is going to be collapsing to a circle on the conic. So topologically, we have this picture here that actually Paul Hiking drew, and then these 2 points here are precisely the 2 points where I cannot, where we have the pencil, where I cannot define this map. The point being is that Fukaya just mentioned here that when we have this torus vibration on the complement of the singular fibers, we have a canonical affine structure on the base that's related to H1 of the Lagrangian fiber. So if we want to see the base of this, and then we have the monodromy around it. That is that corresponds to, if we look at the fiber, corresponds to a dent twist on the fiber. So if we want to embed this picture in R2 such that the affine structure is going to correspond to the standard affine structure of R2, I need to break this monodromy by deleting some fibers. And the way I like to do is always to take, we have, the monodromy has some eigendirection, some invariant direction, and I always like to take a ray from the node to the corner that's belong to this invariant to this line that's invariant under the monodromy. So then if I do this cut here, on the complement of this cut, I have an affine embedding to R2, and then this is going to be described by these pictures, and these are called the base of the almost toric base diagram. And again, the monodromy is totally recorded by the direction of this cut here. Any questions at this moment? No? Okay. So then if we take different, different foliations here on the base, we're going to see that these discs here, they start bounding. So in this picture here, the disc, the torus that bounds, that is monotone, is still the Clifford torus here. But then if I change the foliation, we're going to get the monotone torus lying over this circle here. So it's already one of these mutated torus described by Dimitri and Harold and a lot of people here. That's the Chekhanov torus. So changing the foliation here, corresponding for me to slide these nodes. Therefore we have, but these operations was already described in general, for a general almost toric vibration by Margaret Thimpton. We can always do, if I have a smooth corner, I can always trade my singularity at the corner by a singularity on the center, on the interior of my, of the base of my vibration. And I can always perform these nodal slides, and they will correspond to just different, let's say, Lagrangian foliations, singular foliations of my base. And then, but then in these diagrams, I like to call a mutation that the following procedure. We always gonna nodal slide to the through the monotone fiber, and then I'm gonna want to redraw the same this base diagram representing the same almost toric vibration, but with the cut, instead of going to one side, the cut going to the other side. So I'm just changing, just going to get a new embedding of the base of my almost toric vibration. But instead of being the embedding on the complement of this cut, it's now going to be embedding on the complement of that cut. And then we see that when we perform these mutations, they are in one-to-one correspondence to solutions of the Markov equation. So if I have a Markov triple, which is the solution of this equation here, I can rewrite the same equation in this way, and then it becomes clear that if I mutate A to A prime, then A prime, B, and C solve the same equation that was solved by A, B, and C. So we call this a mutation on the Markov triple equations. And the lemma is that up to rescaling my symplectic form, which means multiplying the size of the edge by this constant here, when I do a mutation on these almost toric diagrams, so let me phrase it better. If I have an almost toric diagrams such that proportionally the affine length of these edges here satisfies a Markov triple equation, and then I do a mutation with respect to one of the nodes. So here I'm going to mutate this node here that's opposite to A. This will, up to some proportional constant, give me a new almost toric base diagram such that the affine length of the edges of these triangles corresponds to the mutation of the Markov. Okay. So in this way, I use this. No, let's not go there. So then I use these pictures to construct this Lagrangian tori as being the torus on the center of these base diagrams, and then I prove later that they are not symplectomorphic to each other. And I'm gonna repeat the proof. I'm gonna talk about the proof after describing the similar phenomenon for all the Pezzo surface. So here is what I say, somehow creating room for doing a toric blow-up. So here, as we said, we don't have a room to perform a toric blow-up, but one thing that we can do is I apply nodal trade for the two corners over there, and I get this almost toric vibration. So now what I'm going to do is I'm going to apply a mutation that corresponds to slide this node here through the central fiber. So in particular, I'm mutating my torus. I'm getting another torus. And then I'm doing this transfer the cut. I'm going to put the cut to the other side. This corresponds here. This edge here is essentially smooth, given by the monotomy that's going to send this vector to this vector here. So what I do is that I chop off the bottom of this picture, and then I apply this monotomy here. So this means that now this edge here becomes straight. This one, which is in the same direction of the monotomy, just slide down, and then the other one just goes where it must go. So we get this picture, and then now what I'm going to do, I'm going to nodal trade these two nodes over here, and perform a mutation with respect to this edge here by sliding it to the other side and redrawing my picture. And what I get is this picture over here. And in this picture, so I would just get this, and it seems that I also want, wouldn't necessarily have to be here, but I also did another trade here. So this is some almost toric vibration for the degree 6 the Pezzo surface, and now you see that we have enough space to perform a blow up of the sites that we wanted and keep our symplectic manifold monotone. And that's what I did over here. Any questions? How much time?
35 more.
25.
Sorry, why did you want to do a blow of this size?
To keep monotone.
Ah.
So so then I can use the numerative geometry. The symplectic, okay, the symplectic manifolds, because here we see that we can come from here we have each one of these. This is already an exception device, so it's a churn one sphere.
Sure.
So we see that it has with respect to this Z2 here that I put on the behind, it has a fine length 2, right? So that's the condition. Remember that the area, the symplectic area, the symplectic area of my curve should be proportional to the churn class.
So you're talking about the condition for the manifold to be monotone, not the Lagrangian.
Yes, okay, so this is the condition for the manifold to be monotone, so we agree that if we chop off something such that the exceptional curve is going to have symplectic area 2, here is monotone. Right. The Lagrangian, I can see a disk living in the class that's orthogonal to this facet, a disk living. I can just needs to look to the, at this point, just don't need to be homomorphic or not. You can just look to the class. A class that goes orthogonal to this facet, those orthogonal to this facet, those orthogonal to this facet. They have the same symplectic area, and they generate relative. Okay, sorry.
So you're just saying it's
in this type, but we also have some Lagrangian spheres here. So I mean, you can.
So Renato, isn't it easier to just say your green dot is at distance 2 from every edge in the affine distance?
From every edge, yeah. And then I guess I would have to also talk about perhaps some Lagrangian sphere to take into account now my relative pi 2. I have more. Okay, I can use the areas of, I already know that the areas of the exceptional curve match in pi 2 of the total space, and then I just complete the base of relative pi 2 with 2 disks, for instance. Yeah, okay. All right, so okay, so now I'm kind of convinced that, well, we can try to keep playing this game and perform several, keep performing blow-ups and remain monotone. So I'm not going to describe all of that, but I want to now, before showing what happens for all the blow-ups, I want to go back to the case of the degree 6 Pezzo surface, and just do one more trade here to get up to this picture that I call this almost this base diagram that has the triangular shape. So at the time that I write my paper, there was two nice things for me to have something with triangular shape. The first one is that I will be able to look at this picture and see this equation here that we recognize for the for the degree 6 Laplace surface, and see that the affine length of my edges satisfies this equation here. And the lemma then would be that if I apply mutations, but now that every time I'm going to cross with all my nodes the central fiber, I'm always going to get some base diagram that has a triangular shape, such that the solutions corresponds to a mutations of this kind of equation here. So this, once you know that there are infinitely many solutions for this equation that was proven by Karpov-Login, I can say that there are infinitely many monotone Lagrangian tories. And the second reason that's not as important now that Tokanov and Pascal have proved wall crossing is that you're going to see that on my proof I really rely on the fact that to be able with my techniques to distinguish this tori, I rely on the fact that the shape of the almost toric fibration was a triangle. Okay, so Pohakun and Prokhorov, they described all the projective space, weighted projective space that could be smoothed into a Del Pezzo surface, and they have this format here, such that the A, B, and C were solution to these corresponding equations here. So this second one here, it appears for the case of P1 times P1, and this one here was the one that we saw on the previous slide, and then one should expect to get a similar one for the next blow up. And so what I want to emphasize here is that somehow here I don't see complex structure in no way. I can see some sort of a limit of the complex structure, but I don't see a complex structure. But it seems that if I want to think that I'm degenerating these nodes all the way to the corner, they are corresponding to some algebraic degeneration of this Del Pezzo surface to the corresponding weighted projective space. No, it's not a proof, but then you can take all these pictures and see that, and claim that, or perhaps hope that, for instance, this Del Pezzo surface, it also degenerates to the orbifold that is described by this polytope here, but without this cut. It's not a proof or anything. It's just it seems to be happening. Okay. So here I'm gonna get. So here's a description for the. As I promised you, you should have some sort of triangular shape, almost toric fibration for the next blow up that will satisfy this. No, it's not so clear to see, but satisfies the equation that was given by Hakim Prokhorov. And here I put in this slide these two equations here. They are just repeating each other. So let me go to the other slides to show what I can have a little bit of the zoom of this triangular shape, almost toric fibration that I can have and get for the other Del Pezzo surface. So for instance here for the fifth blow up, we see that the affine length satisfies this equation here. That was these ABC equations. It's identical to one of them that was given on the theorem of Hakim Prokhorov. But I claim that the best equation to actually describe this picture here has to do what I call PQNR equation. It's not Elsa's PQNR, it's other PQNR. But that is this equation here, such that the number that I get here corresponds to the number of nodes that are together, and the PQNR corresponds to the determinant of these primitive vectors here. And which, if you want to think that you're now degenerating to some sort of limit orbifold, will be the degree of the orbifold singularity that you're gonna have.
Is the question of constructing this orbifold degeneration a local question? I mean, is it enough to just somehow study study once and for all the sort of, the picture near the vertex of the triangle?
I don't think so. You need to understand what happens with the complex structure as a whole. It's a complex degeneration. It's not so.
Okay, I think maybe what you could say is if you have your diagram, then you can just run this gross seeded program. You'll have some scattering diagram.
Yes.
Smoothing this surface, and that I think that all I'm saying is the pictures you're drawing are the sort of pictures that.
But then
you can construct a complex smoothing using that.
But their program gives us the mirror of this surface.
Well, this is the moment polysame, so that's the where you draw the scattering diagram if you're trying to construct a complex family.
Maybe we'll discuss later. But what I understand at least, we have.
It's not local. Yeah. It's a complicated thing.
Okay. Let's talk about that.
But I mean, sorry. Another thing you could say is when you are on the Pezzo surface, there is a general result. There's no local to global obstruction, so you never have to. I mean, if you just want an abstract smoothing, you don't explicitly write it down, then it always exists.
It always exists. So then you can have any of these pictures that I draw here, even if any of these pictures that I draw here, if I remove my cuts, there will be then a degeneration for the corresponding surface to the.
Yeah.
Okay. I didn't know if that would be a theorem or not. That's nice to know. So I'll leave this later. So here is a little bit of the zoo of these triangle shapes diagram, and we have this. I just want you to keep in mind that there is this kind of like PQNR equations that should be the ones used to describe these diagrams. And we're going to come back to it because it's also related to the work of Karpov-Nogin on 3 blocks. They appear on this work of 3-block collection of exceptional collections.
Maybe I can make one more comment. Sorry.
Sure.
Is that I also wrote a second paper with Prokhorov where we have these other equations and
oh yes.
just corresponds to these are actually not weight objective spaces. These are toric
Yeah,
fibrations
it's some
that
sort
have
of orbifold.
yeah, exactly. So it's a quotient of a weight objective space by a finite group.
Okay.
So now that's why you see these other.
We also see this. Okay, so
It's okay.
somehow I didn't pick up the questions for.
It's okay.
For
Yeah.
Actually, I got the questions by myself, and then I looked at the Karpov-Nogin, and they're the same. And but there they prove that these equations here are all the ones that we can get. So this zoo that I'm describing to you here, it's all the possible triangle shaped almost toric fibrations that you're gonna have. So you have 3 for the 7 blow-ups, and you get 4 when you go to the last Pezzo surface. Okay, now how much time do I have?
15 minutes.
15 minutes. So, okay, this is just writing the obvious thing. Somehow I like to because I was so used to look at the affine length of the edges of these diagrams, I prove a lemma that is with respect to the affine length of the edge, and then from this lemma you can just looking at the conditions of these being almost toric fibrations, you can get that it also corresponds, mutations to the PQR equations will also match. So again, if you have this, the affine length of the edges satisfying this kind of more general Markov type equations, you have a notion of doing a mutation on the solutions of these equations, and then if you mutate all the nodes, pass through the central fiber, and redraw the picture, the next the mutation that's going to have, it's going to be it's going to correspond to this mutation here on the Markov type equations. And so the theorem that there are infinitely many Lagrangian tori in all this space that I was able to construct to you that have triangular shape. So the idea is that so let me talk a little bit about the proof that I gave was the following. We look at these almost toric fibrations, and then we see that the boundary, you can look at the surface that lives over these blue cuts here. They will be contact. They actually are going to be some lens space, and we can embed the complement of this. So what the blue part is a lens space, and what's it has a feeling of some rational ball, and then on the complement of these rational balls, n-1, n-2, n-3, you can embed it inside your weighted projective space, symplectically. Then, what you do, I want to count holomorphic curves. So then I pull back the standard complex structure of this weighted projective space here, and then because the space of almost complex structures compatible with the symplectic form is contractible, I can extend these complex structures to the whole symplectic manifold. And then what I do is the next stretching procedure. So I'm going to say the following. Look to any holomorphic disk that has boundary on this torus. And then you can stretch the neck along these lens spaces. So what you're going to get in the limit is some could break in several buildings. But then the point is that we see that what we have here on the top is going to be precisely the weighted projective space, not necessarily weighted projective space, the orbifold, but the complement of the orbifold points of the orbifold described by this polytope. Then what happens is that I can now glue in this orbifold point, and then what I'm going to have is some sort of degenerated holomorphic disk that could have some spheres around, could be described by some spheres like that. But what we have, this now inside the weighted projective space. So what I can do is I can look at the intersection with the edges, and since they intersect positively, it will inside. If I look at the boundary of the disks inside, for instance, so inside edge 1 of my Lagrangian, I look to the boundary of these disks, and I see that because we have positive intersection on the orbifold, it's gonna describe some convex hole here, and all the classes that such that all the classes that are boundary of some holomorphic disk must lie inside a convex hole like that. And moreover, we get for free from Chokodar three holomorphic disks that don't go towards the orbifold point, and then they are counted with multiplicity 1. So I can also guarantee that I have the vertices of this hole that I described inside H1 of the torus. So this completely determines, this then must be the convex hull that I described at the beginning. In other words, the convex hull of the Newton polytope of the potential. And now this is the proof. You just look at what this convex hull is given by these three disks here, and you see that we will have, in the case of CP2, you have a fine length ABC, and in the other cases will just be similar. So then I can distinguish these disks like that. But there is a catch here. Why can't I just then, for instance, here in P1, I can describe for you infinitely many of these tori, such that the orbifold will have this shape. So what's the catch here? This degenerated surface this degenerated disk that I get in the end, it could be that one of these spheres is the edge itself. And then the edge itself could have negative self-intersection. So if my intersection was not transverse to the edge, I could not use positive of intersection to describe the convex hull. So this is why I kind of needed the triangular shape. For the case k equals 1, I have some trick that is just, is the following. Here in this picture, I can construct infinitely many of them. Here I have this exceptional curve with self-intersection -1, and this this one here, you can also prove that it, on the orbifold limit will have negative self-intersection. If I delete this, on the orbifold limit will have negative self-intersection. But this one here, that has Chern 1, which means Maslov index 2, already has the area of a Maslov index 2 disk. So it will not appear as this limit, as some of the spheres of this limit, because here I already have some area. So the intersection with this divisor here will still be positive. Then I would have concluded that I have positive intersection in the limit orbifold with this, and this one. So this does not allow me to describe the whole convex hull, but will allow me to describe some corner. And although this here also has some negative of intersection, by area conditions, it can appear at most, let's say, k times in this sort of configuration. So you can also show that whatever is the convex hull that I'm interested in, it must be compact. So now I can look at the determinant of these primitive vectors, which is invariant under SL2Z, and then I can compute, in this case, that it is going to be actually B prime. So the bottom line is the following. I can prove that each convex hull has a corner with B prime. So I have infinitely many data for the corners of the convex hull. But I only have finitely many possibilities sorry. If I only had up to equivalent to SL2Z finitely many convex hulls, I would not get infinitely many corners. So these also prove that infinitely many of these Lagrangian tori must be distinguished. But doesn't show which one is it. But again, now by the theorem of Tokonov and Paskalev, it's an exercise to prove that each one of these is going to give you a different choice. So I'm over time now, or?
10 more minutes.
No.
No?
Okay. So let me finish. Let me finish with this theorem that I mentioned by Korpov-Nogin. If there is, they describe all of these so-called three-box collections of exceptional collections of sheaves, and then they prove that they must, if I take R to be the rank, so if I'm inside the block, a block of the ranks of the sheaves are constant. So if they have rank P, Q, and R, and N1 and N2 and N3 describes the number of sheaves that I have on the collection E1, E2, and E3, then they must satisfy this Markov, I actually call Markov type 1 equation, there is a type 2. That's of this form. And these are precisely all the ones that are PQR equations that I got with my almost toric polytopes. And they also prove that these are all the equations that could appear that could have some solution. Sorry, all the equations that could have some solutions are precisely the one that I described on my previous slides. And just to finish, since one question perhaps it should be obvious that each one of my almost toric fibration, if the almost toric fibration had m size, m edges with some distributions of nodes, there, in principle, one would guess that there should correspond to these n block exceptional collections on the same del Pezzo surface. I'm not sure if this probably perhaps it's obvious for people on algebraic geometry, but I'm not sure.
It's not obvious, but I have a paper in Duke where.
Okay. So I need to talk to you and then I start citing you way more on my paper. So okay, so this again by hacking it seems to be proven. Okay, it is proven. So let me just finish by relating with Elsa's talk. So she described these monofibers here, and in her paper she also proved that they can compactify to this del Pezzo surface here. And the point is, the following. And she also wrote there that each one of these TPQR monofibers, they can be obtained by some Weinstein handle attachments on the contingent disk bundle of the torus, such that the curves intersect themselves once. And then if you go to my list that I gave you, you're gonna find precisely almost toric fibrations such that the distribution of the nodes are 333, 442, and 632 for the degree 321 del Pezzo surface. So here is an example of the 333 case, and if you look coming from the torus to each one of these nodal singularities, you can see that if you take the cycle that corresponds to the orthogonal here, what you're going to get is it's going to be a Lagrangian. The cycle that collapses here, when you travel over here, gives you a Lagrangian. So it gives you precisely a Lagrangian disk. So this was precisely what was happening on the previous stroke of Harold, that each one of these mutations that one do correspond to these mutations of the Lagrangian disks, and you can keep track of these Lagrangian disks. And so the last thing that I want to say now is the following. You look at this torus on the complement of this divisor here, that I'm going to call elliptic curve, even though I say that I don't see much complex geometry here. I imagine I can always get this is definitely a symplectic torus. So if I look on the complement of that, I get the monofiber, but let's say the right simplex form that one should put on the monofiber is after you attach an infinite end. So, but because so my claim is that even after you attach an infinite end to the complement. So okay, let's see. The boundary of the complement of this picture is a contact manifold that I can now put a positive symplectization of it over there. But my claim is that the torus, the exact torus that I get on the complement, they remain non-Hamiltonian isotopic to each other. And the proof is that if there was an Hamiltonian isotopy, I could put it I could do this Hamiltonian isotopy inside inside the symplectization, how do I describe it? Inside the contact manifold times 0 r for some r. And the point is now that if I then compactify again to a Del Pezzo surface, the torus that I had, the exact torus that I had on the complement, also remains monotone on this new compactification. And then I can use that to tell you that they cannot actually, each one that I construct, they actually give rise to infinitely many on the complement of these divisors. Sorry, I guess I was not very clear about that. And just to make a contrast is the following. And then I'll finish here. So all the tori that I constructed in CP2, they can be put on the complement of a line. But then, if I look inside, so they can be put on a ball. But then if I look inside C2, somehow these tori, they become Hamiltonian isotopic to each other. Because Georgos proved that in C2 you only have Clifford torus and Chekhanov torus. So this is why I'm saying that it's kind of was important that I'm looking on the complement of a smooth anti-canonical divisor, not only an anti-canonical divisor, but one that computes the Maslov index of the disk for me to conclude that these infinitely many tori that I see there are actually distinct. And then I'll finish here.
Questions? Well, if not, let's resume tomorrow morning in different form.